So one can take a look at the original Hutchinson-Huxley circuit that was built right around, from about 2002 to 2004 was when most of the major work was done on this effort. And it has this wonderful structure, basically a 6 transistor device, and a lot is understood about it, a lot has been worked with it. And this works great. So this sort of starts with Ethan Farquhar's original kind of papers on this model. And so this works well. But the question then is, how do I convert this into an FPA design? And so I want to kind of use this discussion to both illustrate a couple of the properties that are going on in this circuit, as well as ask the question, how do I begin to translate sort of classical custom IC built designs into something I would do in an FPA? And this is sort of the core circuit we would have. Remember that you have your channel transistors, both your sodium and your potassium, and then you have your gating variable for your sodium and your potassium structures. Both of these work out very well. Now what you could imagine doing is saying, okay, well, I might implement this in an FPA design. I could implement it with just the transistors, but remember we have, transistors may be almost as plentiful as OTAs. We have a bunch of other routing infrastructure. Does all of this work? And one of the things you notice is that this is a different circuit when we come over to this side. And so the question is why, right? It still has the core of the transistors, so the physics is still there. We're still keeping the potentials in the sodium and the potassium levels similarly. So all of that's there, and the capacitance there. It just turns out that most of the behavior is how am I changing the gating potential? And this requires thinking through what some of the things are that we see in the FPA structure. And there's some benefits and some issues that you run into in almost every design you convert. You run into these problems in one place or another. So like, for example, one of the opportunities is that in my local routing, I've got current sources anywhere I would want to use them. So if I want to add a current source or a voltage controlled conductance where that voltage can even be outside the power supply rail, works great. So that's one option. And you actually see that used in a few places. One, if I use a explicit leak transistor, which sometimes we've used over here, that just happens anytime I need it. So it basically shows up for free. Also, this device here that I'm going to use as basically a conductance to model the H variable, similar sort of thing comes out of the structure. A second aspect is actually then looking at what happens with some of the local routing. And the local routing allows you to connect things, but it also has an issue in terms of setting your complexity and also the questions of capacitance that you might run into in these systems. One of the complexity questions is you realize that most of your area often becomes dominated by the number of lines you need. Well, the number of lines I need for a transistor is 3, right? The number of the count should be 3. On the OTA, it's again going to be 3. So they're about similar complexity, which is an interesting question because normally we'd think of, well, this is 9 transistors plus other devices. But in a practical sense, it's not that much bigger. And so they're much more similar in this sense. The other side of it is that all of the lines actually have capacitance to a fixed potential. So trying to make this high-pass filter having a gain nearly of 1 is going to be really hard. It's going to be, if I just implement it directly, it's going to look like a gain of about 0.1, 0.2. So that's not going to work very well unless I make some use in FPA with very, very large capacitances, which we typically don't make. Usually not needed, but in this particular case you can see it. So I'd want to turn something around. So what happens is this high-pass filter turns out to be, I flip the PFET to an NFET and make it a low-pass filter. I use the floating gate OTAs to help me set the biasing infrastructure. I use another floating gate OTA to help me set its biasing structure. I don't need a lot of gain out of it, so it's not really an issue. And runs it near open loop anyways, and so again that kind of matches the dynamics fairly well. But then it also allows, but I can use these too. It still gives me other OTAs in even that cab to build other structures. So the thing is that you get a circuit that basically is efficiently built in the medium that you're working with and keeps the dynamics that you would be wanting to work with. So I want you to kind of see this because it gives you a sense of what the various opportunities are. Not just in this structure, which is a really neat one to work with, and again, a very efficient neuron that's really hard to implement any tighter than this, but also anything else that you might say, I've got a really neat circuit over, some custom circuit I want to build into an FPA. What are some of the things I might want to think about when I'm actually translating that over into an FPA design?